All right, so we will begin. Welcome again to the seventh and last live session of Learning Geology. Every rock has a story, Watery Worlds. Learning Geology is a community organization that aims to promote geoscience literacy worldwide, and we have been doing this by producing these live sessions and also a variety of geoscience content with our amazing team of editors. So this live session is part of 7 geoscience outreach session, and today's live session is about Every Rock Has a Story, Watery Worlds. So a brief introduction about our speaker, Dr. Ethan Baxter. So Dr. Ethan is a professor at Boston College. He's an amazing science educator. He runs a very famous YouTube channel, Every Rock Has a Story. My name is Mohammed Qasim, and I'm a co-founder at Learning Geology, and I'm also a PhD student at University of Prince Edward Island in Canada. So in today's live session, you will learn about stories of rocks and minerals and how these rocks and minerals have been shaping our planet Earth and also the solar system. I will now hand over to Dr. Ethan Baxter.
All right, Qasim, thank you so much for the invitation and for the introduction. I'm really happy to be here. I didn't know this was the very last one of these sessions, but I'm happy to be a part of it and really excited to be interacting with the folks that are joining online. So I want to get started by just saying that we'll be talking about rocks and minerals. I'm sure everybody's heard about rocks and minerals, and for me, when I was starting off learning about rocks and minerals in school and even in college, a lot of emphasis was put on identifying them, giving a name to the rocks and the minerals. And an exercise that I like to do when I teach my earth materials class at Boston College is something I'd like to do an abbreviated version of just with the audience together before we dig into the presentation. So I did bring a bunch of rocks. We're going to get to see some, but here's one right here. And we would normally do this in a classroom setting, but just at home, just take a good look at that. Just as you're looking at it at home, I just want you to answer in your own head, answer a very simple question. What do you see? Tell me what you see. So as you're thinking about that question, you might notice a shape. It's a bit of a triangular shape. You might notice that black color, maybe a dull shine. If you had it, you could tell it's a little bit heavy. So those are some of the answers you might have to that question. What do you see? And I like to start with that because almost anybody can look at something and make those observations, and that's the beginning of identifying what the rock is. But what a geologist sees is what I want to talk about today. And when a geologist looks at this rock, I can see beyond the colors, the shine, the shape and the heaviness. And when I look at this rock, what I see is a young child looking up at the night sky late at night, a clear night, looking up with wonder and noticing something flashing across the sky, a bright, bright light flashing across the sky. We call that a shooting star. And I imagine that young child looking up with wonder and wondering, asking, maybe, is it just possible that I could reach up and grab that shooting star and hold it in my hand, which is what I'm doing right now. This is a shooting star, and I'm holding it right here in my hand. As a geologist, I look at that and I imagine 4.5 billion years of history that this object has witnessed, has seen. This is older than the planet itself, older than the planet Earth. So the story that it tells is one of those early formative times in our solar system, literally before the Earth had fully coalesced, all the way up to that present moment where we can look at wonder into the skies. So those are the stories that I want to talk about. And as we get into the presentation, we'll be focusing on some of the stories that rocks tell about water. But it's so critical, I think, for everybody to understand that rocks and minerals are so much more than just what we see with our eyes. It's the stories that they tell. And so I think I'll start the presentation and share my screen. Here. Kasim, is that correct, or should I flip it?
Yeah, maybe you can flip it.
How's that?
Yeah, now it's good.
Okay, very good. So let's get into the discussion that I'm hoping to have with everybody today. So as I just said, rocks and minerals are so much more than just identifying what they are. I want to get into the stories. The stories behind those rocks and minerals are what make them interesting, exciting, and worth paying attention to. And it's those that the eyes of a geologist, the stories that a geologist can see, are what I want to bring all of us into together. Now, the title, as Kasim mentioned, is Every Rock Has a Story, Watery Worlds. What I've chosen today is to use water as a thread that will tie all of these stories together. And I'll tell you more about why I chose water in just a minute. But as Kasim also mentioned, during COVID-19, I started a YouTube channel called Every Rock Has a Story. This was something I started because I couldn't be in the classroom sharing these stories with kids of all ages. And so we started alone at home, actually right here, up until this last season 3 was actually just nominated for a regional Emmy Award. So we've come a long way since the beginning. And the purpose of the YouTube channel is twofold. It's to inspire everybody out there, children in particular, about the stories of the earth, and really to help all children understand that science and geoscience is for them. It's for everybody. So we can talk more about this, and I'll be mentioning various episodes of Every Rock Has a Story throughout the presentation in case you or children you know want to take a look at those afterwards. But I focus on water. And another question that you can all answer at home, we'd be raising hands if we were together. You can ask yourself, have you ever heard of water? And I hope everybody is saying, yes, of course, I've heard of water. You can all answer that question. I don't have to explain to you what water is. I don't have to explain to you where to find it. And another question I could ask, can everybody think in their mind, can I think of at least one reason why water is important to me or important to the earth? Again, you can all come up with, I'm sure, multiple reasons why water is important. Water is something that brings us together. Geoscience, rocks and minerals, I'd like to show are things that can bring us together and bring different parts of the earth together. And water allows us to do that. As we go along, we're going to talk about how water can be a shaper of those watery worlds. We'll talk about how water can be a source of life. We'll talk about how water can actually live inside rocks and minerals. We'll talk about how that water can then be a trigger for natural disasters. Towards the end, if we have time, I'd like to talk about one way in which water can be a responder to changing climates. And just to emphasize again, that's just the very beginning of the stories that rocks and minerals can tell about water, about the earth, about the environment, about the solar system. So that's a bit of a roadmap. Let's get into this as we talk about the connections that we can make through rocks and minerals and through water. And let's start with this image. This is an image that I expect many of you can recognize. This is one of the most famous places in the United States. This is the Grand Canyon in Arizona, a spectacular landform. Actually, the first time I got to visit it was last summer when I was filming this episode, episode 68 of Every Rock Has a Story. My co-host in that episode is pictured there. Her name is Becky Flowers. She's a professor from University of Colorado. And she's collected rocks from the very top to the very bottom to figure out the answer to this question. Just how and how long did it take to carve the Grand Canyon? Here, and I'm hoping you can see me on the corner of the screen, that's called the Kaibab limestone. And that's the very top of the Grand Canyon that we're standing on here at the top. That represents the story of this rock is an ancient flooded continent About 270 million years ago, all or most of the interior of the United States was underwater, high sea level. That was before the Colorado Plateau had risen. And that limestone was formed on that shallow sea at that time. Well, Becky's also sampled rocks from the very bottom. And this is a sample from the very bottom of the Grand Canyon. This is a granite. This is almost 1.8 billion years old. And so one of the exciting things about the Grand Canyon is that grand history, almost 1.5 billion years of history shown in those layered rocks, those strata laid down by a range of processes, including the water of those ancient seas 270 million years ago. Of course, I imagine most of you know what has carved the Grand Canyon. It's the Colorado River. It's still down there right now. You can't see it in this picture because it's so incredibly deep. But the mighty Colorado River has been carving and carving that river for perhaps as much as 70 million years, based on some of the new data that Becky has collected in certain parts of the Grand Canyon. So this is the force of water chipping and carving and ripping away at that sedimentary rock for tens of millions of years to create this incredible landform. So when we think about rocks, when we think about even landforms made out of rocks like this, the story that a geologist sees here is a 1.5 billion record of deposition and 70 million years of carving this canyon by a river. What I want to do is move on to another landform as we talk about rocks and some of the landforms that are left. This is a picture of a delta. You may recognize that this is the delta of the Mississippi River. So a delta, as a reminder, is the sediment that gets deposited and fanned out where a river meets the open sea, river meets the water. And this is the spectacular Bird's Foot Delta, emptying out at the bottom of Louisiana as it flows out into the Gulf of Mexico. That characteristic, some people call it a bird's foot, or I like to think of it more as a tree-shaped pattern. That tree, the branches of a tree fanning out, depositing all that sediment into the open sea. This is a bit of a false color satellite image, but all that green, that's the dirt, the sand, and the mud that's been fanned out and deposited into the ocean. So when a geologist sees that shape, that pattern, that delta, yes, we can talk about the shape and the branches, but the story is a story of a river depositing sediment into an open sea. And that's where I want to take this forward. Let's train our eyes now. Let's look at some other deltas up. And this reminds me, along the way, I want to talk about some rocks. That is from episode 42, which talks about how rivers are moving sediment and dirt from the rivers into the oceans. You can see some beautiful ripple marks, wave ripples preserved from that sedimentary rock. I'm going to hold up here another rock. This is a sedimentary rock, and I hope you can see that on the top of the screen. Is that easy enough to see, Kasim, would you say? Good. What I want you to see there is not so much the red color, but those lines, those stripes. Those are very, very vivid sedimentary layers. This is a coarse sandstone, exactly like you might find in a river. This, of course, was laid down by an ancient river. So a rock like this, a rock like those wave ripples in this delta tell us a story of ancient water or modern water, in the case of the delta, flowing into an open sea. Here's another delta. As we get used to the different ways that deltas can look. This is a beautiful delta flowing. This is a river flowing north, and see that really vivid tree shape or branching out shape pattern. Very, very clear. We see how that sediment, all that brown sediment being splayed out and deposited into the sea. This is the Yukon River flowing north into the Arctic Sea. So there are deltas all over planet Earth, as you know. So we're starting to train our eyes to recognize these features. Let's look at another delta. This one's a little different. First of all, we can vividly see that tree branch kind of a shape, can't we? Very, very vivid. The branches of that tree carrying that sediment out. We can see the sea in the distance. What I hope you're noticing, or what I hope your wheels are starting to turn on here, is that this delta appears to have dried up. The river doesn't even really make the ocean anymore, does it? This is a river that seems to have lost its supply. The water no longer flows or barely flows. So this is a little bit different. A geologist looks at this and says, this looks like a place where a large river once flowed to create this huge delta, but the water is dried up. And that begs the question, why? What has happened? I'll give you a hint by showing this image. That's a city. That's the city of Las Vegas. If you can see the black pyramid there with its spire down on the bottom right, that's Las Vegas. What's remarkable about this river delta, that's the river delta of the Colorado River. That's the same mighty Colorado that for 70 million years has been digging down, or rivers like it have been digging down, down, down to carve that Grand Canyon. And for some reason today, it doesn't even make it to the sea anymore. And the reason is people. We're taking water out of the Colorado River to provide water to cities and communities like Las Vegas. In fact, Nevada is just one of the states that's extracting water from the Colorado River. We see water being taken out for California, Utah, Arizona, Colorado, and other uses. Some of that water is being used in places like this. That's the Hoover Dam, one of the most significant pieces of architecture in the United States, the Hoover Dam, right near Las Vegas. And as you probably know, this doesn't just dam the river, but along the way, the Hoover Dam is taking energy from that flowing water down through that structure, creating hydroelectric power. So this next slide is an interesting one. This is from 2015. This doesn't get updated that often, but this is the USGS's account of what we use water for in the United States. And you can see in orange, the big piece of the pie, that's the use of water in power generation, hydroelectric power, and other uses of water related to the generation of energy. So we're taking a lot of water to create energy in the United States. The other big one here is that green piece of the pie, that's for irrigation. That's to grow food. So if we think about what are humans doing with water, it's a lot more than just drinking water or public supply or taking a shower. Irrigation and energy generation are the big ones. And if you've ever wondered if human society was powerful enough and strong enough to fundamentally transform the surface of the earth in ways that the earth would otherwise take millions of years to do, well, we're doing it right now with the Colorado River, taking that something so powerful to carve the Grand Canyon, and now it no longer even reaches the ocean. I want to show you one more delta. And this is a delta that maybe some of you have seen. It's become a very famous delta. There are some hints on this image as to where this delta is located. And I'll cut to the punchline on this one. This is a delta on the surface of planet Mars. This is in a place called Jezero Crater. And what's remarkable here, we can even just see that snaky ancient river coming in from the top of the screen, that fanning out shape of the sediment being deposited into what must have been an ancient sea in front of us, and that very, very vivid fanning out delta form right there. It's pockmarked with some craters. Imagine being the first geologist receiving this image, this satellite data from the satellites that are orbiting Mars right now, and recognizing that shape and say, oh my goodness, I've learned what that shape is based on my studies on planet Earth. That is a delta. And recognizing that the story of the delta is more than just its shape. The story of a delta is a place where a river deposited sediment into a large body of water. This is another image. This is a topographic image. The huge blue circle, that is a giant crater that was filled with water. We can see the river. Can you see my cursor on the screen? Up here? Perhaps. But we can see the shape of that river channel snaking in and then depositing the delta. The delta itself is, part of it is circled in a black circle there. That's what we were just looking at. There's even a place on the other side of this crater where a river flows out again. So this was an actual dynamic system. We had a big crater filled with water, a river coming in, a river going out. Now, this is an artist's idea of what this probably looked like at some time in the past. But what's happening now, as some of you may know, is we have some very clever geologists, they're robot geologists, that have traveled to Mars, and they're exploring this watery world on planet Mars right now. This is a picture taken by the Curiosity rover. There's Curiosity on the cover of an issue of the Elements magazine, all about the minerals on Mars. And this was a picture taken by Curiosity, not at that delta, but at another location. And I think the most important thing to see here isn't so much that characteristic red color that we think of for Mars, but down on the bottom right of the screen, those rocks there with those vivid layers, flat, layered rocks, very much like the one I showed you here, those flat layers. When a geologist sees flat layered rocks like that, that indicates a sedimentary environment. Those are sedimentary rocks on Mars. And one of the common ways to make layered sedimentary rocks on our planet is through the action of water. Wind could also lay down layered sedimentary rocks. But this Curiosity rover wasn't done. It made another very critical observation. It made many critical observations, but in locations like this, not only did it see layered sedimentary rocks, it has an XRD instrument, that's X-ray diffraction, on board that's able to actually identify the specific minerals that exist. And it found a mineral called clay. We've all heard of clay. Clay is extremely common, very commonplace on planet Earth, but clay is a remarkable mineral because in order to make clay, you need water, liquid water. There's actually water inside the clay mineral structure itself. So Curiosity finding clay, recognizing layered sedimentary rocks, that satellite image of a delta, all of those commonplace observations together tell a story of an ancient watery Martian past. We got to go back 3 or 4 billion years to get to that ancient history. But this is a remarkable story that was only possible because of geologists bringing together these rocky observations and understanding those stories, not just saying, oh, there's clay, but recognizing the story behind it. The Perseverance rover landed a couple of years ago. This is the most recent robot geologist on the surface of Mars. It landed in February of 2021. It spent the last couple of years roving around and up onto that delta. And its primary mission is to collect rocks. That circle there in red, that shows a tiny little drill hole that the Perseverance rover drilled into those layered rocks right there at this delta. That's exactly where Perseverance has landed. And it's pulling out tiny drill cores. Each one of these rock cores is about the size of a piece of chalk or a finger. And you can see right there inside that little that brass fixture is a red core of Mars rock. That's a live picture from the surface of Mars. And Perseverance is collecting those samples and getting them set for another mission 10 or 15 years from now to pick up those samples collected by Perseverance and bring them home to our laboratories. Episode 73 is about this mission. And that's another scientist friend of mine, Tanya Bosak at MIT. Hers is one of the laboratories into which these samples will be brought. She's one of the project scientists telling Perseverance where to sample, which rocks to collect. I want this one, I want that one. And she'll be one of the labs that's able to receive those samples. Tanya is expert in recognizing the signs of early life here on planet Earth. No one expects to find macroscopic fossils or bones on Mars. No one's found any evidence for life on Mars. The evidence for water is tantalizing suggestion that there could have been life. If there was life on Mars, it would be microscopic. It would be microbial. And as you can learn about in this episode, one of the specific types of rocks on our planet that Tanya is expert in is called a stromatolite. And this is a beautiful stromatolite here. The stromatolite is a sedimentary rock, and it's got weird wavy structures or lumps or bumpy structures rather than flat layers. And these stromatolites were basically created by ancient bacteria, cyanobacteria on planet Earth 3.5 billion years ago in some cases. She knows the physical and the chemical signatures that those ancient microbes left on Earth, and that's what she's going to be looking for on Mars. Are there stromatolites on Mars? Probably not. But she's literally going to be looking for structures like this or the geochemical remnants thereof. So that's a fun episode. And before we shift gears to another story, if you don't want to wait 10 or 15 years to see those chalk-sized samples that were collected from Mars and brought back by an incredible NASA mission, you can watch episode 51, which is about this rock. And this rock right here, which is in a box, I always say if a geologist has a rock in a box, you know it's got to be special. And this one certainly is. This is a real rock from Mars. This is a Martian meteorite that was knocked off the surface of Mars and made its way through outer space and landed on planet Earth. So we actually do have some samples from Mars that we've been studying. And so we've learned a little bit about Mars via the natural processes that have brought fragments of Mars like this into our laboratories. But the future is really exciting. So we've talked about how water can be a shaper of our planetary surface, the shaper of the surface of Mars, and how it even can be a catalyst for life, certainly on this planet and maybe on other planets. I want to shift gears and I want to talk more about the rocks that record water as a source of life. This, as some of you may recognize, is a spectacular image. It's an image from the internet that I borrowed, but this is the very bottom of the ocean. We're back on our planet now. And on the very bottom of the ocean in 1977, for the first time, the Alvin submersible, a little submarine, a manned submarine, went to the bottom of the ocean and discovered this. These are called black smokers. These are hydrothermal vents where hot water that's been heated by the Earth's interior is circulating from the ocean, getting heated up and spewing back out into the ocean bottom. And in so doing, delivering nutrients, delivering energy. They're very hot. And even delivering minerals in the form of that black smoke into the submarine environment. This episode called Submarine Adventure has another scientist friend named Heather. She's getting into the Alvin submarine right there, preparing for a voyage to the bottom of the ocean where she collected black smoker rocks. This is an example of an ancient black smoker from an ancient seafloor environment, and probably hard to see there, but these have fine layers of gold and gray and black, which represent zinc and copper and sulfur and lead that are spewing out in that black smoke. But the incredible thing about these underwater environments, these are places that marine scientists years ago would have assumed were completely dark, completely cold, completely devoid of light. The sun doesn't shine at the bottom of the ocean. But these deep sea hydrothermal vents, this hot water entering the bottom of the ocean, is providing the energy and the nutrients to catalyze incredible life. Life like giant 4 to 6 foot long tube worms, 1 foot diameter white crabs, white squids, all powered by this heat and the nutrients in those black smokers. And I've got a video we can play in the background. The video may not take it home, but that's okay. The black smokers are unusual. These are images from what we call a white smoker. And whether you're seeing stills or the video, this is very similar to the black smoker environment, except that the stuff coming out is white. These chimneys are white. And the kind of biology that is stabilized here is even more remarkable. And this image these videos were given to me by a friend, Susan Lang, who was at Woods Hole. And she pilots a remote control submarine. And this little vial of white powder right here is actually a bit of the rock from this lost city hydrothermal field that she brought up to me as sampled by the Jason submersible. I always like to say that one of the best things about being a geoscientist, being any kind of a scientist, is when you get to do science with your friends. I make a lot of friends. I have a lot of great colleagues. Science it can be lonely, but it's also a place where you can make a lot of friends and learn from each other. We all learned from Susan in collecting these rocks and these samples and then bringing them back to the surface. I'm going to skip past the video and move into the next part of our conversation. So we've seen rocks from the bottom of the ocean, rocks from these remarkable biological environments that record the catalysts for life. We've seen rocks like the ones that the Mars rover is seeing in outer space. I want to bring it now to our planet, and I want to take the next step in our voyage of a global rock cycle. The sedimentary rocks we've talked about so far and the actions of water are all happening at the Earth's surface or in the bottom of the oceans. And for most folks, when we think about water in geology, that's where we think about. We think about the surface of the Earth. Where we're going to take this now is we're going to take rocks and water deep into the Earth. It's often a forgotten part of the classic rock cycle, but it's an extremely important part of the rock cycle. And it starts with getting water into some critical rocks. And we can start with the mantle. As you probably recall, the very outside thin layer of the Earth is called the crust. That's what we're all standing on right now. That's where we live. If you go below the crust, the big thick layer below that is called the mantle. And the mantle is made mostly of a beautiful green rock that you can see a picture of right there called peridotite. Peridotite is the green rock of the mantle. This episode number 8 is about the green peridotite of the mantle. And here is that same rock that's pictured there. This is what we call a xenolith or a foreign rock. It's foreign because this is not a rock that belongs in the crust. It's not from the crust. This is from the mantle. And xenoliths can be ripped out of the mantle in violent volcanic eruptions from great depth. And those xenoliths are spewed onto the surface so that we can hold in our hand and study actual chunks of the mantle. So we don't have to wonder what the mantle looks like. We have chunks of it, even though we've never dug that far. What's interesting, especially in the oceanic crust is pretty thin, especially near the mid-Atlantic, the mid-ocean ridges where it spreads apart. And those same ocean waters that we talked about before in the hydrothermal vents get circulated down, deep down, even into the mantle beneath the ocean. And when we add water to the peridotite of the mantle, we create another rock. And that rock is called serpentine. And there's a picture of serpentine. I have that same sample right here. Serpentine is also green, but it's kind of a dull olivey green. It's called serpentine because structurally at the microscopic level and even at the macroscopic level, it kind of has a shiny, almost like a lizard or serpent-like kind of twist to it. That's manifest at the microscopic level as well. But this is loaded with water. If you take peridotite and you add water, you make serpentine. Now this serpentine doesn't look wet, right? It doesn't look like it's got water. If you cracked it in half, it's not like the water is going to spill out. If you shake it, it's not like you can hear the water. The water is bound in there inside the structure. And a question that I think we want to ask is, all right, so there's water in here, but tell me how much water is in this? The way we're going to get it out is by heating it up, and we'll do that in a few minutes. But just how much water is in here? I call this one of my water rocks, an ocean rock, ocean water rock. Well, this has about 15% by weight water, 15 weight% water at the high end can be inside serpentine. Now, I like to visualize things. So if we realize that the density of most rocks is almost 3 grams per cubic centimeter, and the density of water is just 1 gram per centimeter, that means by volume, that water is going to end up being a lot of this. And I've done the calculations, which are easy to do. And this is what that looks like. Right now, this much serpentine contains that much water. It's remarkable when you look at it, a little bit more vivid in person, but you can see representation on the screen. That is a ton of water held inside this rock. And what's critical is that when this serpentine grabs that water, and there are many other types of rocks and minerals that hold water inside, when those water rocks are then brought into the Earth's interior, that water plays a significant role in driving what happens next. Episode 10 is all about this water rock, this serpentine, this ocean water rock, and it's a good one to watch to really flesh out this idea. But let's talk about that now. Now that we understand that water can actually live inside rocks and minerals like serpentine, let's talk about what happens when it gets subducted into the earth. And what it can do, that water, that same water, the source of life, that same water, the shaper of those watery worlds, in this context, that water can be a trigger of the most significant natural disasters that can befall our planet. This image here, of course, this is a map of the globe, and all those black dots, as you may be able to guess, those are a representation of all the earthquakes that would happen in, say, a given year on planet Earth. Earthquakes don't just happen anywhere, they're concentrated along those plate boundaries, different types of plate boundaries. The ones that I want to focus on, where we see that incredible density of earthquakes, are found, for example, around the Ring of Fire. The Ring of Fire, I love that Johnny Cash song, The Ring of Fire. But this Ring of Fire is around the Pacific Ocean, where all those blue lines you can see represented are where the oceanic crust is subducting or going underneath the lighter continents above. Those subduction zones are where the oceanic crust and mantle are going underneath the continents, and in so doing, water rocks like serpentine are bringing a lot of water down there too. And what happens, and this is a bit of a busy figure, but this would be representation of a subduction zone going under, in this case, Japan. So Japan is a place where we have earthquakes and volcanoes as well. They exist there because as those water rocks, and it's not just serpentine, there are many other water rocks, bring their water down. As they descend, water can be released from some of those water rocks, and the release of water is part of the reason and part of a triggering mechanism that allows those plates to slide and can allow those earthquakes to happen. And so that triggering mechanism related to the release of water from certain watery rocks and minerals can give rise to some of the most devastating earthquakes on our planet. We can think about the 2011 Tohoku earthquake in Japan that caused mass devastation, and also a tsunami wave that was just devastating on a very frightening day now more than 10 million years ago. That same friendly water that was a catalyst for life can do devastating things as well. Deeper down the subduction zone, other water rocks can take the water even further. Serpentine would be in this category, can bring it even further down. And at those greater depths, once it gets heated up enough, that serpentine will literally release its water like it's being boiled out. And that water can get into the mantle wedge above it, and that can create melting and catalyze the most explosive volcanic eruptions and what we call arc volcanoes. This is Mount Fuji, this is Mount St. Helens, this is Mount Pinatubo, all these giant volcanoes erupting huge plumes of smoke and ash and water. Here's a picture of a volcano in the Aleutians erupting. You can see that explosive ash coming out the top. This looks like a fairly small eruption. But I like to think of the fuel for these giant eruptions as derived directly from these water rocks, like serpentine that we've already talked about. This episode number 29 is about this water rock. This is a beautiful powder blue rock called a blue schist. And blue schists also carry water deeper into the earth. And some of the minerals inside it, like those whitish rhombs are called lawsonite, are also loaded with water. Blue schists release their water when they get below that volcanic zone, and that fuels the volcanoes. So when we talk about volcanic gases and spewing out ash, the power, the fuel in creating those volcanoes and making them explode so powerfully is literally water coming from those water rocks. So we're doing the rock cycle, but we're taking it down into the earth. Another fun episode, another fun story of water is this one, number 70, which is about Yellowstone National Park. Yellowstone National Park was once a supervolcano, and it will be again someday in the future, although that may be hundreds of thousands of years in the future. But Yellowstone is a sleeping giant. It was a supervolcano, and I like to think of it as resting right now. And that supervolcano, when it blows, and blow again it will in hundreds of thousands of years, it again will be powered by those magmatic waters, that literal steam that will blast high and far and send ash covering over probably half the United States. What's happening right now, as we discuss in this episode, is the Earth there is literally breathing in and out as the supervolcano rests. My friend Bex Bendick is a geoscientist, and she is monitoring with her organization called UNAVCO the breathing, the literal inhale and exhale of the supervolcano. She has sensitive GPS instruments that can measure as the Earth puffs up and as it puffs back in. And every time it exhales, we get geysers. Where you find geysers and hydrothermal fields like in Yellowstone or in Iceland, that's how a volcano sleeps and breathes. It's literally letting off steam. And it's a good thing it's letting off that steam, because that kind of keeps that volcanic system in check. And geologists like Bex are watching it breathe in and out over time. I do have a sample that a colleague of Bex collected many years ago from Yellowstone. And this is a volcanic tuff, T-U-F-F, a tuff, but that's what volcanic ash looks like after it's solidified. Fragments of obsidian and some other minerals like feldspar and quartz are in there, but all that orangey gray, orangey red color is that ash which is solidified into this volcanic remnant. This one's probably about 70,000 to 100,000 years old. And this represents just a little, maybe just a little startle of that sleeping volcano. Not a super eruption, but just a little snort maybe as it was resting and snoring. We haven't had one of these for 70,000 years. So these are some other ways that water and rocks come together and tell these stories, which can be frightening stories sometimes, of natural disasters. The last thing I want to mention before we move to a final topic is some of the work that we've been doing in my group. So I've talked about water rocks, how those rocks are vehicles to bring water down into the deep earth in those subduction zones, and why that water is so critical to creating volcanoes, to catalyzing earthquakes, to literally creating continents and continental crust like Japan or all the other continents in the first place. We owe the existence of the continental crust to that water being brought down in subduction zones. Well, we're studying that process by going to places such as pictured here in the Italian Alps, where ancient rocks that had been subducted, so slabs of the ocean that actually went down deep through a continental collision and a tectonic accident, were thrust back up to the Earth's surface. That mountain in the background is a spectacular peak called Monte Viso, if you live in Italy, or Mont Viso, if you live in France. It's right near the French-Italian border. It is entirely made of serpentine. It's entirely made of this water rock. That's ancient ocean floor. And now it's up on the surface. Actually, this is a chunk of serpentine with a darker green color that we collected from Mont Viso. That's a graduate student of mine. Her name is Anna Gerritz. She's holding a big chunk of serpentine that she collected up there. We're studying the story of water in subduction zones by looking at the rocks that lived that experienced those processes. This episode number 22 is about my favorite mineral, which is garnet. And I like to think of garnets as the tree rings of the earth. And that picture right there is of one of the absolute most spectacular samples I've ever seen in my life. Certainly one of the most spectacular garnets I've collected in my life. If you've heard of garnet, you probably think of it as having a red color. Most garnets are in that sort of red to pink spectrum. It's the birthstone of January. If we have any birthstone fans out there, happy birthday if you're a January birthday and garnet's your birthstone. But that garnet right there is, first of all, enormous. Second of all, it's not red, it's white. I've got it right here again. It's got just a pale pinky hue to it, but this is a white garnet, bigger than the size of a softball. And if you look very careful, and I think you can see it better on the PowerPoint than here in person, you can actually see it has growth rings. You can see it has concentric rings of growth. Garnets, when they grow, they can grow very, very slowly. This particular garnet from a place in Italy called Dora Myra, which was subducted to depths of over 100 kilometers before it came back to the Earth's surface, records at least 6 million years of growth history. We know that because in my laboratory, we've dated each one of these concentric growth rings. So I like to think of garnets as a tree ring chronometer of those long-lived tectonic processes. And here's that same example, that same garnet with its visible growth rings and a tree with its visible growth rings. Everybody knows about these. They're very familiar. We can find them in our, in our yards, in our parks, read about it, dendrochronology, tree ring chronology. Yep, you count back those days, you can get hundreds of years chronology in a single tree. Add some other chemical information, you can reconstruct past climates over that time span. Well, garnets have that same kind of growth zonation, from the inside out. And we can actually peel back those layers one at a time with some different chemical tools and reconstruct ancient tectonic processes spanning millions or even over 10 million years in a single crystal. The reason that we're focusing on garnets like this one and where Anna is because of our knowledge that when garnets grow, the reactions that form the garnet are also releasing that water. So even though the water has mostly left rocks like these, by studying the garnet is a time capsule of all that water that was released. So we can use our geochronology by dating the span of garnet growth. We can use thermodynamics to reconstruct the garnet forming reactions. And we can reconstruct exactly how much water was being released, how fast, and even recognize changes in the rate at which water is being liberated in these ancient subduction zones. And that's why we're focusing places like this. Just got one last theme that I can't help myself but discuss before we open it up to some questions, if you have any. The last rock I want to talk about is ice. And a lot of times when we talk about ice as being a rock, there's a combination of surprise, rolling of eyes, but I'm here to be very clear. Ice is absolutely a mineral. It is a solid crystalline material formed in nature with a definite chemical composition. That chemical formula, by the way, is H2O. It's just solid water, and it's a mineral. And when you have a whole bunch of crystals of ice, you have what we call a rock. Here's a picture of a spectacular ice sheet. This is Greenland, and that's all rock. And the only rock you can see in that image is ice. On our planet, ice is special because it's right near its melting point. So sometimes it melts, as we see it doing in this waterfall. Sometimes it freezes. On other planets like Mars or some of the icy moons from the other planets, water is always in a solid form. And they can be one of the most common rocks on the surface of those planets. So it's important to realize that ice is just another rock. And what's happening on our planet is the ice is melting. And again, sometimes the videos don't work well over a Zoom like this, but whether you can see the video motion or just a still, this is a fantastic image of a river of water cutting a canyon through a rocky landscape, and the only rock you can see is frozen water, ice. So it's just an interesting dichotomy of liquid water and its solid equivalent around it. This might be a rocky landscape we might see on some of the icy moons of Jupiter or Saturn, but this is right here on our planet. This was taken by Professor Mark Bain, one of my colleagues at Boston College, on Greenland. And this is what's happening every summer. We get rivers of melt water as that ice begins to melt. Those flow out and coalesce, and over time, some of that water is escaping out into the seas, which leads to sea level rise, which I'll give a nod to in just a second. A great visualization, which I'm hoping you can see, to drive this point home, that ice is just solid water, it's a rock. um, is this visualization right here. On the left, we're seeing the same picture we just saw. And on the right, that's another river of a liquid flowing through its solid equivalent. That's lava flowing through solidified lava, which we call basalt. That's a picture that I got from the internet. That's probably from either Iceland or Hawaii. And so somehow when we see that image of the rock, we say, oh yeah, that's lava. That's a liquid lava flowing through rock. That's basalt. That is the exact equivalent as the similar melt and solid scene that we see on the other side. There's my friend Mark Bain jumping over one of those rivers of molten rock in Greenland. And there's a fun picture of me sampling some molten rock as I did in Hawaii a number of years ago in 1999. This, by the way, is the lava rock that I collected on Hawaii in 1999. It's one of my favorite rocks because I made it myself. This rock wouldn't have existed quite the way it did if I hadn't collected it and stuck it in a bucket of water. This is in episode 5 if you want to hear that story. That was a great memory. Of course, we're worried about the melting ice sheets these days because it's flowing into the seas. When Greenland melts, when Antarctica melts, it makes the sea level rise, and that can have global implications. This is what's now become a commonplace scene in some low-lying areas, for example, in the capital city of Bangladesh, Dhaka, within just a meter or so of sea level. Dhaka is a place where rising seas, because of the melting of ice sheets in Greenland, are becoming a very, very real challenge. And where I live in Boston, when I talk about this for my students, I think it can be easy to look at an image like this and say, oh, well, that's frightening, but that's not happening here. I don't have to worry about that. Episode 62 with Juliet Sefton, another scientist from Monash University, is all about rising sea level and what she's doing to study it. This is a picture of my hometown. That's Boston, Massachusetts. And that was a storm in 2018, a winter storm. It coincided with the king tide. And if you know Boston, this is right at the seaport. The aquarium museum is right around the corner. And what you're seeing there isn't a puddle. That's the sea. That's sea level. And it's risen up and flown into the Seaport District in Boston. And this is becoming more and more common right here in my town. So we're far beyond a point where the melting of the rock that we call ice is just somebody else's problem in some faraway place. This is happening in Bangladesh. This is happening in the United States. This is happening all over the world. And it's too late to stop paying attention to it. And that's why cities like Boston and others around the country are making predictions and projections like this. When we look at the rate of ice melting as the ocean starts to rise, and we look at the topography of our coastlines, what's going to be underwater in a big storm in 2050, in a big storm in 2100, just like we saw in 2018. It's going to be more and more of our cities and our populated areas are going to be inundated. So as I hope this audience knows, the issue of warming temperatures, melting ice, sea level change, these are issues that are already real. They're at our doorstep. I want to wrap up there. I want to say thank you to Kasim again for the invitation. I hope you've enjoyed seeing just a few of the ways that rocks can tell stories about the earth, tell stories about water, and how that water brings us all the way through the entire earth system, from hot to cold, shallow to deep, and even to other worlds. And again, I'll just leave you with this. I hope some of you check out my Every Rock Has a Story channel. It has 73 episodes now. Each episode is about a rock and the story that it tells. And we can probably put a link to the channel in the chat. But I will stop my presentation and see if there are any questions out there.
Thank you so much, Dr. Ethan, for incredible presentation.
You're very welcome.
We do have a couple of questions from our viewers. So first question is, how is water existing below the planetary surfaces detected by props?
How is it existing below planetary surfaces? And it was the last part of the question.
Yeah, detected by props.
Is it in rocks?
Yeah, detected
Yeah.
by props.
Yeah. So if I understand the question, I guess what I'd say is this: when we think about the crust of the Earth is the most dynamic part of the Earth. It's also the closest to the surface, and there are an incredible range of rocks that are holding in them an incredible amount of water and other important Earth's surface chemicals we might talk about. Let me give you some examples. This is a metamorphic rock called a schist. This is the most common type of metamorphic rock. It's formed in almost any mountain forming event on the planet. The interesting thing about a schist like this one, this used to be, before it got squeezed and heated up, this used to be sediment on the bottom of the ocean, mostly clay. And we call it politic sediment. Politic sediment accumulates in piles a kilometer thick on the bottom of the ocean. And that clay, as we talked about when we were talking about Mars, the clay itself has tons of water inside that structure. Well, when continents collide, it's that politic sediment on the bottom of the ocean that gets caught up, gets squeezed, metamorphosed, and turns into this politic schist. This is loaded with water. All these micas, muscovite and biotite and green chlorite, they have up to 5 weight % water in this rock right now. And there's some garnets there. We've actually worked on this rock. This is from a place called Townsend Dam in Vermont. These garnets take about 3 or 4 million years to grow, and they release during that time a couple weight % of water from this rock in the crust. Other sedimentary rocks can get down into the crust. I will tell one other story. If you go deeper than the crust, and this might have been where that question was getting, when you get into the mantle, we typically think of the mantle as a pretty dry place. You know, that peridotite that I showed, here again, that beautiful green rock, there's no water in this. The olivine, which is the green mineral, no water. Pyroxenes in black, no water at all. There might be a little, just a tiny trace of water, but we think of the mantle as nominally water-free, nominally anhydrous. But here's a fun one for you. There are some rocks like this one right here, and this is a very special rock called a kimberlite. For those of you who might not have heard of a kimberlite, it's named after Kimberley, South Africa, which is one of the most famous kimberlite eruptions occurred. It's a volcanic rock. Kimberlites have extremely great deep origins. They come from the very, very deepest parts of the mantle, or from very deep in the mantle, and they erupt with such ferocity, in large part powered by water and a little bit of carbon dioxide, that they can rip chunks of the deepest parts of the mantle out of the mantle. And that includes minerals like this. That's a little diamond. It's a pretty big one, although it doesn't look like it on the screen. A beautiful, shiny diamond. It's not a very pretty one. It's all dark and gray. But these diamonds are what I call our messengers from the deep. Diamonds are just pure carbon, but the pretty clear diamonds are the ones we want to put on our rings. But for a scientist, we like the messy ones, because inside this diamond, there are little bits and inclusions of the other minerals from the deep parts of the mantle. A few years ago, a scientist by the name of Graham Pearson, who's a professor in Alberta, Canada right now, found a diamond with greatly deep origins, found a mineral inclusion inside of it called ringwoodite, which only forms at incredibly great depths. And he's able to look at the ringwoodite, and he was shocked to discover that the ringwoodite in the diamond from the deep part of the mantle had almost 2 weight % water. And that was a complete mind blow. That is to say, we now have evidence, thanks to that work, thanks to this diamond messenger from the deep, that even the deepest parts of our planet, and perhaps other planets, can actually hold significant amounts of water. And that, it turns out, is a big deal. Great question.
Thank you. Next question is, are there any geological changes observed in Yellowstone currently?
So the the issue about Yellowstone that I would say is it's changing constantly. So that breathing of the earth is something that happens over the days and weeks. And so that episode 70 is a really, whoever's asking this question, episode 70 is fun. You can actually see these GPS instruments. It looks like a little, the big fancy GPS, but it's anchored to the rock. And they've got GPS stations all over Yellowstone. And they can actually measure changes in elevation or changes in land surface less than a centimeter. So the GPSs literally record the earth puffing up. And then when water is, literally exhaled, it can puff back down. So there's a regular growth. So in terms of, do we see things changing? It's changing every single day. But the change is normal and predictable and well regulated. And that means that Yellowstone is just sleeping. There are no indications of magmas getting ready to erupt. There are small earthquakes frequently. But again, what scientists like Bex Bendick and her organization called UNAVCO are charged with is looking and evaluating very carefully what is the normal state of play of this dynamic system. So it's changing every day, it's changing every week, but they know what normal changes look like. And if someday, and it's very unlikely that that day will happen in human history, we've been waiting 70,000 years for the last little eruption. That's what formed this rock. If something starts to change and those changes become bigger or unpredictable, then there's something new brewing. So that's a great question. So the answer is, yeah, things are changing all the time, but we understand those changes and we'll be prepared if something a different type of change happens. I hope that helps answer that question.
Thank you very much. Next question is, how did you date a growth ring of a garnet?
Great question. So this is the major emphasis of what we do in my lab. So to make a fairly long story short, I guess it's a 6 million year long story short, but this one is a great one to talk about because it's so big. Of course, garnets aren't usually this big. And so we do what I'll describe at a much finer scale. But we can either see those literal growth zones like those tree rings with our eyes, or more commonly, we have to make a chemical map. So what we'll do is we'll collect a garnet, we'll slice a concentric disc right down the middle of that garnet. We think of it as roughly a sphere. And then we'll make a chemical map, and that map will illuminate those concentric growth zones. And then what we do is we have a fine drill, and we drill out, following that chemical map or those literal contours, we drill out one ring at a time. We take that ring of garnet, each concentric ring, we dissolve the garnet in our laboratory in hydrofluoric acid, which is the only acid that's powerful enough to dissolve a rock like garnet. And then what we do is we extract two particular elements. And the elements we extract in our laboratory are samarium and neodymium. They're rare earth elements. You might have heard them in some conversations about rare earth resources because they're very important for modern technology. Samarium is radioactive, very slightly radioactive. And when it decays over time, it makes some neodymium, very particular isotopes of samarium and neodymium. So again, to simplify things, in each growth zone, if we measure how much of that parent samarium is there, and if we measure how much of that daughter neodymium has been produced, we can figure out how long that clock has been ticking because we have a great understanding of the rate at which that parent samarium decays into neodymium. And so these, we would call a radioactive radiogenic pair, a parent-daughter pair. We use samarium neodymium to tell these stories. You might have heard of uranium decaying to lead or potassium decaying to argon. These are other of these radioactive parent-daughter pairs that we use to constrain Earth history. And we've been sharpening our tools with garnets for almost well over a decade now, to where we can do this at very, very high precision. And not just say, when did the garnet form, not just how long it grew over, but actually recognize oscillations in the growth rate. This one's remarkable, and we'll be talking about this science at a conference in Lyon, France this summer. It took a couple of million years for this thing to get going. And then 85% of this garnet grew in just a couple 100,000 years, which geologically is fast. And then the rim slowed down again. So we can even see it accelerating as it goes with the tools that we've developed. I hope that was a good answer for that question. Episode 22 can help flesh out that story as well.
Thank you very much. I have already shared a link of your YouTube channel, and I would highly recommend everyone to go watch some of these episodes. So there is a comment, great discussion. I am a retired geologist, but every time I contemplate the earth and its complexity, it moves my soul. I did not realize how much water was in serpentine. Wow. And there is yeah, please go ahead.
Amazing. Absolutely amazing.
Yeah, and there's I guess the last question. Is there any interest for resource mining on other planets at this time?
That's a really interesting question. Yes, I think is the short answer. Although it's not yet practical for a host of obvious reasons. But I think the way I want to leave that question, well, first of all, that's what episode 20 is about. We actually have an episode that talks about that. There was a movie, I guess it was 10 years ago, won the Academy Award called Avatar. I'm sure you've all heard of Avatar. You've probably seen this with the blue people, and they were on the moon of Pandora. And you remember the ore they had on Pandora? It was called unobtainium, one of the greatest geology names ever, unium. And of course, human civilization went to Pandora to mine the unobtainium, bring it back to Earth. And it's an interesting movie from a geopolitical and environmental standpoint as well. Anyway, that was science fiction. The director of Avatar is a guy named James Cameron. He's a very, very good director, and he's a very wealthy guy. Shortly after, or maybe during the time that Avatar was being filmed and produced, James Cameron was one of the people that started an asteroid mining company. You can look it up. So that is not science fiction. James Cameron himself was one of the lead investors in an asteroid mining company called Planetary Resources, and their plan was to send spaceships not to other planets, but to the asteroid belt between Mars and Jupiter, which is loaded with, would-be shooting stars like this one, which are incredibly rich in a huge range of elements, iron and nickel, but beyond that, in particular things like the platinum group elements, and actually water as well, which is a separate issue, the value of water out there for space exploration. But there was at least one other asteroid mining company that was started. My understanding is that those have now petered out at this point. It just wasn't a financially viable and technologically viable project at this time. But it's an interesting example of where art and imagination literally led to someone saying, hey, maybe we should get serious about mining on other worlds. And I certainly don't know, but I would say that if and when we set up a base on the moon, which seems likely, and if and when we set up any kind of an operation on Mars, I am supremely confident that people on this planet will already be well along the way of thinking about what are the extractable resources that exist on these other planetary surfaces or even asteroid surfaces, and how could we get them? And maybe I just wrap by saying we have a history in our civilization of solving problems, like where are we going to get all our energy, and coming up with magical and incredible solutions, like we're going to get coal, 300 million years worth of energy that the Earth has created, and we're going to burn it to make that energy. These incredible solutions that we've come up with sometimes have consequences. Like we've recognized that the burning of coal has created the situation with global warming we're facing today. So as we as a society start to contemplate, should we mine the asteroid? Should we mine planet Mars if we could get there? Or anything else? The challenges that we face require bold solutions. But those bold solutions must also require very careful evaluation to make sure we're not making other mistakes along the way. And we're getting better about that as a society, but we're still not perfect. And I think the geoscientists of the future need to have both that bold imagination and that creativity to think big, but also the care and the responsibility to really evaluate the consequences and prepare for them and mitigate them. So great questions. I really enjoyed these questions. I feel we should have done questions the whole time, but I love this opportunity to share some of my favorite stories about rocks, and hope you guys have enjoyed it too.
Thank you very much. There is just a general comment. This is fascinating. I'm learning so much. Thank you, Ethan, for your fantastic presentation.
You're very welcome.
And there are also some general comments. People are just thanking you for your amazing presentation. And just a last question we just received right now. Is there a concern for destroying natural system balance on the planets?
On planet Earth?
Yep.
I assume. I think the answer has to be absolutely. I mean, we have already seen that our activities here on the surface of planet Earth, here mostly on the land surface, and we could point to many things, but I think the one I just mentioned is our thirst, our need for energy, and the fact that most of that energy over time has been through the extraction of fossil fuels. That has impacted another part of the Earth system, which is the atmosphere, adding more carbon dioxide gas into the atmosphere. Every bit of carbon dioxide gas in the atmosphere is like putting another blanket, warming the Earth. And we're putting on a lot of blankets, and we're putting them on really fast. The Earth is very good at moderating its temperature through other rocks that we won't have time to talk about today. It takes a while for the Earth to catch up. And what's remarkable about what's happening today is actually not that CO2 is rising. It's actually not that it's getting hotter. The Earth's had way more CO2 in the atmosphere than it does today. It's not that big a deal. And it's been way hotter than this in the past too. The problem is how fast it's increasing. That's what's unusual. That's what's remarkable. That's the problem. The Earth, give the Earth 1 million years, it's going to catch right back up and re-equilibrate those systems. But right now, the changes are happening so fast because of human activities that we're drying out the Colorado River, putting too many blankets on the Earth, heating up things too fast. We're melting too much ice. Sea levels rising too rapidly for the Earth to catch up, and maybe even for humans to stay ahead of it. So yes, we are worried about the balance of these different parts of the Earth system. But that's where modern geoscientists come in, and we bring that creativity, that imagination, that understanding of all the different parts of the Earth, not just the atmosphere, not just the ocean, not just the land and the rocks, but all those parts working together. That's where our solutions are going to come. And I'm confident we're going to find those solutions as scientists and as policymakers. It's a little tricky, but we are going to find those solutions. And it's going to be, those of us who are, watching this Zoom or out there thinking about these issues and coming from all the different parts of the Earth system. I like that question about an imbalance between Earth's different parts of the natural system. It's clear that the solutions that are going to make a difference won't be focusing in just one area or one aspect. We're going to need multiple solutions, and those solutions will involve multiple different parts of the Earth system and how they work together. And I think that comes back to this theme that I tried to start with in this presentation, that rocks are just one way that things come together. Water is just one way that different parts of the Earth come together. And those connections were what I find the most fascinating part about science.
Great answer. I definitely agree with you. And there's also a comment from one of the viewers that's why an essential part of geoscientist education needs to be art, history, philosophy, and other humanities. Yeah,
and I'll comment on that to that last point. As a professor at Boston College, I wholeheartedly agree. We, for our geology majors, for everybody who comes to BC, we have a very strong commitment to the social sciences and the humanities, to philosophy, even to theology, and finding, where all of these decisions and choices fit in a broader context. And I completely agree. I think we need scientists that are also humans and recognize the responsibility that we have as a society and communicate these scientific questions and challenges and opportunities to that public. That's how we're going to make the changes that we need to, and we will make those changes.
Well, thank you so much. I think we will now end this session. Thank you so much, Dr. Ethan, again for incredible presentation and sharing your knowledge with us. And also, I would like to thank all the viewers to join this live session, and also our previous live sessions, which we have been doing from last month. The recording of this live session will be available on the Facebook page right after we end this live session. Thank you again, and we wish you a great rest of your day.
Thank you.